Hi, everyone. Welcome to CS 159, Data-Driven Algorithm Design. Today, it is a great pleasure to have Bobby Kleinberg and Devon give the lecture on structured procrastination for automated algorithm configuration. Bobby is a professor of computer science at Cornell University. His background is in theory of algorithms and algorithmic game theory. A little bit of trivia. He was actually my co-advisor when I was a PhD student at Cornell. So I really enjoyed my time at Cornell working with him. Devon, who will be giving the second half of this lecture, is a PhD student at the University of British Columbia, where he has become interested and is working on data-driven algorithm design over the past year. So we'll start with Bobby. Take it away.
All right. Thank you so much, Yusung, for inviting both of us to give this presentation. Really excited to tell you about the structured procrastination algorithm. In terms of the format of this lecture, I will be presenting the first half, which is based on an IJCAI 2017 paper with Kevin Leighton-Brown and Brendan Lucier. The algorithm in that paper was later improved in a NeurIPS paper that Devon joined us for, and he will be presenting that work in the second half. So the union of these two presentations is really joint work with Kevin, Brendan, and Devon, but the paper I'm presenting here is just with Kevin and Brendan. You might be wondering about I always like to have a piece of artwork on the opening slide of my talks. You might be wondering why this building, which I invite somebody to tell me what building it is and who is the architect. And then I will tell you what it's doing here on my opening slide.
Am I allowed to answer, or is that cheating?
I suppose you're allowed to answer, Yusa.
It's Falling Water.
Correct. Yeah, one of the most famous houses in America. And yeah, so the principle of the algorithm that I'm going to be presenting to you is based on procrastination. And I discovered the following amazing story about falling water. So Frank Lloyd Wright was 67 years old. And he designed this house in 2 hours. So the story is he was commissioned to create falling water in 1934. And the businessman who commissioned it took him to the site in November of that year. And afterward, Frank Lloyd Wright wrote to him and assured him that he had been working on the plans, but in actuality, he had not drawn a thing. The following September, he gets a call early on a Sunday morning from the businessman who says he's going to be visiting before lunch and can't wait to see the design. And so Frank Lloyd Wright got into high gear, and in 2 hours, with a group of extremely nervous apprentices looking on, he drew up the plans in the time it took for his commissioner to drive up from Pittsburgh. And yeah, as I said, this is one of the most famous houses in America. It's, for example, listed among Smithsonian's 28 places to visit before you die. I have never been there, but I do hope to get there at some point. Yisong, who's lived in the Pittsburgh area, I hope has visited Falling Water.
Yes, it is quite amazing.
Okay, so that's what procrastination is all about. What is algorithm configuration? In this work, we're going to be looking at algorithm configuration with a specific objective, namely running time. And our motivation is really thinking about how to configure solvers for hard optimization problems that AI people often attack using powerful heuristics and the power of large computing resources. A typical workhorse solver, CPLEX, has about 80 parameters that the user can set. And most of these parameters control some aspect of the algorithm that it uses to search for solutions to these NP-complete mixed integer programs that it's being asked to solve. I've listed the names of some of the parameters here. I don't actually know what actually any of these parameters means, but from looking at the keywords in these names, it gives you some idea for the gestalt of what an expert algorithm configurer has in mind when they're setting these parameters. That they control something about the search strategy for making in other words, they're hyperparameters that control the search strategy for doing things like branching or picking a local search direction or deciding when to terminate one part of the search and backtrack and try a different branch of the tree. And so the basic goal that we're going to study is if you want to tune a solver like Cplex to run fast when solving problem instances sampled from a distribution from which you have examples, how can you rapidly discover a relatively efficient configuration for solving new examples drawn from that same distribution? So this is a type of learning from experimentation problem. It has similarities to the multi-armed bandit problem, and I'll spend a significant amount of time talking about those similarities and presenting some background material on solving multi-armed bandits before we get back to algorithm configuration. Before I do, I want to just highlight some properties of this problem domain. So one is it is minimally structured. The parameter space of algorithm configurations is typically not a nice convex set. That's because the parameters are a mixture of continuous and discrete. Also, even for the portions of the parameter space that are continuous, the objective function cannot be relied upon to vary continuously as you vary those hyperparameters. It sometimes has some jump discontinuities. The objective also varies wildly, so it's not uncommon for the solver to take less than 1 second to solve one instance and more than an hour to solve others. And also good configurations can be quite rare. A random configuration is often orders of magnitude slower than an optimal one. And this has important implications for designing a good search procedure for algorithm configurations, because it's wasteful to spend hours and hours confirming that a bad configuration requires hours and hours to solve each problem instance, when that time might be better spent searching for the 1 in 100 diamond in the rough configuration that only takes a minute or two to solve each of those instances. So beginning the process of formalizing this problem, we're going to have a set of n configurations denoted capital N, a probability space of problem instances denoted capital gamma. In a typical application, this probability space would just be the uniform distribution over a finite set of benchmark instances that the designer of the problem has produced. A remark about problem instances, the algorithm configurations are often randomized algorithms. In cases where the solver uses a stream of random bits to make random choices along the way, I'm going to interpret the random bit stream that the solver accesses to be part of the problem instance. So that is to say that a point in gamma is really an optimization problem that the solver is asked to solve, paired with the source of random bits that it uses for making its random decisions. That means that the reason I'm making that modeling choice is it means that the solver's behavior when presented with a single instance in gamma is deterministic, because all of the randomness that it relies upon is incorporated into the data contained in a sample point of gamma. Okay, so for that reason, the running time of configuration I on instance j, R of ij, can be interpreted as a deterministic value, not a random variable, even if I is a randomized algorithm. And we're going to assume that these running times are numbers between 1 and 2 to the beta. Okay, so I've scaled my units so that 1 is the minimum.
Bobby, you may have cut out slightly. All right, everyone, sorry for the uh, technical difficulties. We will be back shortly.
In the meantime, if there are any questions from the first 1.5 slides, I can try and field them now while we wait.
Sure. Maybe while Bobby is getting back, maybe a few questions about your experience with the algorithm. So, you know, in your experience doing this algorithm configuration on, let's say, Cplex, you know, is it true that you can get wildly dramatic orders of magnitude differences in different tunings of the hyperparameters?
So I guess I have two answers to that. One, I know that this is true. But two, I don't personally have a ton of experience using these configurators yet in practice. So part of it is setting up experiments like that is sort of a huge engineering task, you know. So that's something we're looking at now in our group, is sort of getting large scale experiments running. Probably, you know, for sure on Cplex, but probably on some other solvers too. But Cplex is obviously the first place to start, and even sort of then doing some sort of comparisons with like SMAC and these other heuristic methods. But you know, like Cplex is a tool we use in our research group a lot, and for sure this is something that that we found. Even the sort of default out of the box parameter setting can be like wildly worse than an optimized version.
And just so I guess the audience has a sense of how this algorithm works, at a high level, it works by choosing to run a certain configuration for a certain amount of time and then freezing it. And then doing some sort of censored statistical analysis of how long it might take.
Yeah, exactly. So the sort of key idea is that the algorithm is like lazy and procrastinates. So it tries to solve, you know, it has a configuration in mind, and it tries to solve a problem instance, a particular integer program. And if it turns out to take longer than it had hoped, it gives up and like saves that instance for later with doubled cap time. So it says, okay, you know, once this instance becomes kind of starts to look easy again, then I'll try it again with this increased cap time. But for now, I'm not gonna do this anymore.
Right. So basically, it says if running this process takes longer than k seconds, I'm just going to cut it off at k. And then at some point in time, I will increase my tolerance k to something longer. And that's, of course, that exactly how to choose that kind of decision is part of the theory of the algorithm design. But that's the high level idea.
That's exactly the high level idea, and really the tool for choosing this is a queue, and you sort of just enqueue instances and dequeue them as you're going, and if you fail to solve it, you re-enqueue it with an increased cap time.
Yeah, I wonder how this like translates to lessons about life.
So I don't know if Bobby's going to talk about this, but
Yeah.
structured procrastination is an idea from a philosopher at Stanford, actually. So for sure it has implications.
Fascinating. Hey, Bobby, you're back.
I am back. So sorry about that.
No worries. We were just chatting broadly.
I appreciate Devon suddenly taking over. Yeah, so I was going to do some drawing on my iPad, which is why I was insisting on connecting that. But I think in the interest of time and not having more technical difficulties, I'm just going to screen share from my laptop and not worry about the iPad. Okay. Another inelegant thing is that, well, never mind. Here comes a key feature of the model. So because runtimes can vary so widely, we want to give the user of the algorithm configuration procedure an ability to set a timeout threshold that says, I'm only willing to spend a maximum of theta time units waiting for configuration I to solve J. If it doesn't solve in that time, I'm just going to cut it short and get a truncated measurement of the running time. So the cost when that happens is the min of Rij and theta, and you don't observe the running time Rij if you cut it short at theta. Instead, you just get a one-sided observation. You know that Rij is greater than theta, but you don't know how much greater. And that ability to time out the runs of the configurations is what gives this problem its distinctive flavor compared to other sequential experimental design problems that I have worked on. So just a bit of notation, I'll say R sub theta of I is the expected theta capped running time of configuration I on a randomly sampled problem instance J. And P sub theta of I is the probability of completing before time theta. And I'll just use opt, OPT, to denote the minimum average running time of a configuration in the universal set N. So a key definition is we say a configuration is epsilon delta optimal if there is some timeout threshold theta such that the average theta capped running time of I star is within 1 plus epsilon factor of opt, and the probability of completing is at least 1 minus delta. Otherwise, I star is called epsilon delta suboptimal. I feel I should probably motivate this two-parameter notion of optimality. If I had just said that the average running time of I is within 1 plus epsilon factor of the optimum, that would be the standard notion of approximate optimality. Instead, I have a bicriterion approximation where I'm allowed to give I star a handicap that on a small fraction of instances delta, it doesn't have to finish, and I'm only going to average its running time on the ones where it does finish. And the justification for doing that is in cases where the runtime distribution is extremely skewed, it could be that the average runtime of I star is mostly determined by the 1 in a million event that it takes 1 billion time units to complete. You know, its expected runtime might be 1,000, whereas the opt is only 100. But you know, the whole reason that I star has an expected runtime of 1,000 is that there's a 1 in a million event that it's going to take 1 billion time units to complete. All the rest of the times that you try running it, it only takes 5 time units to complete. So, okay, in that case, if you don't try out I on a million different problem instances, your data is going to show you that I always runs in 5 time units. The next best contender always runs in 100 time units. And there's no way that you would think that I is inferior to the other one. And unless you want to tolerate algorithm configuration procedures that have an obnoxiously large running time, you have to be sort of tolerant of these cases where a configuration with an extremely skewed runtime distribution is selected as being near optimal because we haven't seen the black swan event that makes its expected runtime really bad. Actually, this whole discussion about black swan events is the prelude to a longer philosophical discussion about whether average runtime is really the objective one ought to optimize, that has occupied countless conversations between me and Kevin, probably countless squared conversations between Devon and Kevin, and is a really interesting subject that I am just going to evade by saying for today's lecture, average runtime is our objective. And with that modeling decision, inevitably comes this slightly weird two-parameter definition of optimality, of approximate optimality. Having said that, our goal is to find an epsilon delta optimal configuration with probability at least 1 minus zeta for some specified failure tolerance probability zeta. And we want to minimize the expected running time, here denoted by expected running time. This problem bears some similarities to the multi-armed bandit problem that I presume many of you have heard of. So I want to spell out the similarities and differences. In multi-armed bandits, we have a set which are now called arms instead of configurations. We have some sample space, which we can call gamma. And arm I has a reward distribution whose value at sample point j could be denoted Rij. And a variant of multi-armed bandits, which is called best arm identification with the pack objective, asks us to find an arm which is whose expected reward is at least the optimum minus epsilon, with probability at least 1 minus zeta, and minimize the expected number of arms that we need to pull before settling on one which is probably approximately optimal. When I spell it out this way, I hope the similarities between the two problems are quite apparent. So let me focus on the differences. A minor difference is that in algorithm configuration, we have a minimization rather than a maximization objective. This difference is really immaterial because I could just, everywhere that you see me on the multi-armed bandit slide saying reward, I could just negate it and call it a cost, and then this problem has a minimization objective as well. Then you would want to find an arm such that R of I is less than or equal to optimum plus epsilon. Okay, a more significant difference is that we have a multiplicative notion of approximation in algorithm configuration, and that we are assuming the cost of pulling an arm varies widely, like over a scale of factor of 1 billion or more. You know, number 2 and number 3 really go hand in hand. So the more customary assumption in multi-armed bandits is you normalize rewards to be between 0 and 1, and then you search for an arm which is epsilon additively close to optimal. And the key thing that I want to observe here is that if we try to shoehorn algorithm configuration into that format by saying, you know, these algorithms that generally solve in less than a minute, but sometimes could take a day, I'm just going to normalize all the running times to be between 0 and 1 by measuring all of them in units of days. Okay, but then, you know, searching for an algorithm that on average runs in only 1 minute and deeming something to be near optimal if it's within 10 seconds of the optimum running time, you know, that amounts, when you scale things so that 1 unit represents 1 day, that amounts to a normalization where the epsilon that you're trying to achieve is like 10 to the negative 4. So, so yeah, you're going for like 10 to the negative 4 regrets. In a bandit problem, those of you who have studied these things know that that's going to take an absurdly long number of iterations to get the average regret down that low. It'll be like 100 million or a billion arms that you have to pull, even if it's a 2-arm bandit problem, if you want to ensure regret less than 10 to the negative 4. So rather than do that in normalization, we allow the costs to be unnormalized. We let them vary over an extremely wide range, and we tolerate multiplicative rather than additive approximation. The final key difference that I've already highlighted is that we have theta capped and censored observations. Okay, so that completes my comparison of the models. Here's an outline of what I want to do in presenting these models. So algorithms for both of these problems depend crucially on some facts about the way that averages of independent, identically distributed random quantities approximate the true mean of that distribution. In effect, we need quantitative strengthenings of the weak law of large numbers that don't just say that in the infinite sample limit, the empirical average of a bunch of IID observations approaches the true mean, but actually talk about how closely it approximates the mean after a finite number of samples. So I will first present some key tools for reasoning about distribution of random averages. Then I will briefly present to you or remind you of, if you've seen it before, the analysis of an important algorithm from the multi-arm bandit problem called UCB for upper confidence bound. Then I'll get to the algorithm configuration problem and present our algorithm, structured procrastination, which in some sense is a generalization of the UCB algorithm, or at the very least, I could say draws inspiration heavily from that algorithm in its analysis. Are there any questions at this point before I move on to the technical part of the lecture?
I do have a quick question. One other difference, it seems, is that the reward and the cost are directly tied to each other in this algorithm configuration problem, whereas that need not be the case in multi-arm bandits.
I completely agree, and thank you for adding that to the list of differences. Yeah, that is kind of so. Yeah, I can't say it any better than what you just said, you saw. Anybody else? I realize I don't have the participant window open, so I couldn't even...
I'm monitoring the chat window, and if anyone raises their hands or sends a message, a question through chat, I'll interrupt.
That's great. So let's begin with the Hufting bound. Here's the weak law of large numbers, which says if x1, x2, etc. are IID random variables with finite expected values, and if xs bar denotes the empirical average of the first s samples, there's a typo there. It's 1/s times x1 through xs. Then for every positive epsilon, as the number of samples goes to infinity, the probability that the empirical average deviates from its expected value by more than epsilon tends to 0. And the Hufting bound makes a stronger hypothesis about the random variables, namely that they have support constrained to an interval of length 1. And in exchange for making that stronger assumption, it draws a much stronger conclusion. This probability does not just tend to 0, but it tends to 0 exponentially fast in the number of samples and at an exponential decay rate that depends only on the number of samples and the length of the support interval being 1, but does not show any dependence on the actual distribution of x1, x2, etc. Okay, some commentary on this bound in case you have not seen it before. So one way of thinking about the meaning of this bound is as a sample complexity bound on the task of predicting the mean of a distribution by averaging S samples. If you want your prediction to be within epsilon of the truth with, say, at least 95% probability, the Hefting bound shows that order of 1 over epsilon squared samples suffice. And this, by the way, is the correct order of magnitude. So there's an information theoretic lower bound that matches up to a constant factor, this upper bound, on the sample complexity of mean estimation to within epsilon. The other key thing to notice is that if you don't just want constant probability of success, but high probability of success, the good news is that the failure probability tends to zero exponentially fast as you push the number of samples beyond 1 over epsilon squared. So that's the sample complexity viewpoint on what the Hefting bound is saying. The other viewpoint one can take on it is a confidence interval interpretation. So for that interpretation, it helps to define rho to be the square root of log k over 2s for some parameter k. And then the Hefting bound implies that if you draw S IID samples, average them to get the center of an interval, x sub s bar, and then draw an interval of radius rho around that midpoint, the probability that it contains the true expected value of the distribution is at least 1 minus 2 over k. Okay, so for any specified k, if you want probability 1 minus 2 over k of getting the population mean inside a confidence interval, you should set your confidence radius to square root of log k over 2s. This is an extremely useful principle to know for what comes next. So without further ado, here is an algorithm based on upper confidence bounds for solving the epsilon zeta pack learning problem for best arm identification. So the strategy is we play each arm once. That's just to make sure that from then forward, the empirical mean of each arm is well defined because we're not dividing by 0. And from then on, what the algorithm will do is it'll maintain a confidence interval for each arm of the bandit centered at the current empirical mean observation. And the confidence radius that it uses when arm I has been sampled S of I number of times is written on this slide. So as you might have expected from the previous slide, it has a square root, it has the log of something in the numerator, and it has 2 times the number of samples in the denominator. And so at the beginning, when I've only played each arm once, the confidence intervals are quite wide. As time goes on and I accumulate more data, the arms that have been frequently played tend to be the ones that have higher means. Their confidence intervals shrink to show that I have obtained a greater amount of training data, so I'm relatively more confident that I know where the true mean is. And in the state illustrated by this colored picture, you can see that the 4th arm, colored purple, has a smaller empirical mean than the empirically best one, but it has a higher upper confidence bound because I must have extracted fewer samples from the purple arm thus far. So the UCB algorithm will prefer to play the myopically suboptimal purple arm in order to acquire more training data about it and increase its confidence that the green one is actually better than it. Finally, when interpreted as an algorithm for identifying the best of n arms, I should specify at the end of the search, how do you select an arm which is putatively near optimal? The way the algorithm does it is it's an anytime algorithm that the user may interrupt at any time. It will always be prepared to make a guess what the best arm is. The guess becomes more accurate and more probably accurate the longer you let it run. But whenever the user ends the search, it will just guess the arm that it has pulled most frequently up until that point in time. So that's a description of the UCB algorithm. I next want to delve into how we analyze it. And the first observation is that we can use the Heffting bounds to say that the probability of the true mean lying outside of the confidence interval for any arm at a time when I have sampled it S of I number of times is less than zeta over 2n times S of I to the negative 2. And why is it less than that quantity? Because that weird logarithm that I put in the numerator of the fraction was rigged so that when I plug the confidence radius into the Heffting bounds, the right-hand side of that inequality would be exactly zeta over 2n S of I to the negative 2. So now let's say that a full execution of the UCB algorithm is called clean if at all times every arm's confidence interval contains the true mean of its distribution. And using the union bound, we can see that the probability of an unclean execution is bounded by the sum over all arms, sum over all values of S from 1 to infinity of the probability of the event that arm I has a messed up confidence interval at the time when I draw the S sample from it. And here I've written down that sum, and using the fact that the summation of S to the negative 2, S from 1 to infinity is pi squared over 6. If you, pi squared over 6 conveniently is less than 2, so it more than cancels with the 2 in the denominator of zeta over 2n. The n arms over which I'm applying the union bound cancels with the n in the denominator of zeta over 2n, and we get that the probability of an unclean execution is less than zeta. So to justify that the UCB algorithm meets the epsilon zeta pack objective, now I just need to show you that if a clean execution is stopped after some specific point in time, after it's had enough time to draw sufficiently many samples, then it never outputs an arm which is further than epsilon away from the optimum. So let's see how that part of the analysis looks. If arm I is epsilon suboptimal, whenever I pull it in a clean execution, we must have 2 times rho of I is greater than epsilon. Here's a place where I would love to have my iPad screen and be able to draw on it for you. Instead, I'll just wave my fingers around in the air, and if you see a video of me and my slides, you have to interpolate between my fingers and the slide. So the optimal arm has a confidence interval. In a clean execution, we're assuming that the true mean of the optimal arm is somewhere in that interval. Arm I has its own confidence interval, whose upper endpoint at the moment that we pull it is greater than or equal to the upper endpoint of the confidence interval for the best arm. Okay, but the true mean of I lies below the true mean of the best arm. So inevitably, that means these two intervals must overlap. In fact, it means that the true mean of the best arm is sitting somewhere inside the confidence interval for arm I. And since the width of that interval is 2 rho of I, that means the interval must be wide enough to span the gap between the means of the best arm and arm I. Okay, once we have that 2 times rho of I is greater than epsilon, we just plug in the formula for the confidence radius, do some algebra, and extract an upper bound on the number of samples. See, the confidence radius shrinks the more samples I collect. So now I'm just solving an inverse problem of, if I know that the confidence interval is still wider than epsilon over 2, what upper bound does that give me on the number of samples of arm I? And the upper bound turns out to be order of log n over zeta times epsilon to the negative 2. Incidentally, the epsilon to the negative 2 should not surprise you if you remember what I said about the sample complexity of estimating the mean of a distribution. Because anytime you're trying to estimate the mean of something within epsilon, there's usually an epsilon to the negative 2 that comes into the sample complexity. Okay, so now if I run the UCB algorithm for a number of time steps, which is at least log n over zeta times epsilon to the negative 2 times n, and the execution is clean, then I can be sure that the arm which has been pulled most frequently has been pulled more than log n over zeta times epsilon to the negative 2 number of times. On the other hand, I showed that in a clean execution, an epsilon suboptimal arm can never be pulled more than that number of times. Ergo, after this time capital T, if the execution is clean, the most frequently pulled arm must be epsilon optimal. That finishes verifying the epsilon zeta pack objective.
I just want to make a quick comment related to previous lectures in this class. So in previous lectures in this class, we have guest lecturers talk about well-calibrated confidence intervals, where they want these confidence intervals to hold not only for a single time step of interaction with the environment, but across the union of all time steps of interaction with the environment. So when Bobby talks about an execution being clean and being able to upper bound the probability of not clean across all time steps of the interaction, it's very closely related to previous concepts of well-calibrated confidence intervals.
Nice. Thank you, Yi-sung. Now that I know you've been talking about well-calibrated confidence intervals, I ought to come clean and say the heavy-handed way that I am using the union bound here to bound the probability of a clean execution is not, information theoretically, it doesn't give you the optimum sample complexity for getting well-calibrated confidence intervals. And so more sophisticated algorithms can get slightly narrower but still well-calibrated confidence intervals by using principles a little more sophisticated than the union bound over arms and time steps to justify that the confidence interval is never violated. In fact, in Devon's half of the lecture, I think he'll show you one case where we can use a tool a little more sophisticated than the union bound to save information theoretically on the number of samples needed to get a certain confidence bound. Okay, I want to pinpoint some key themes of the analysis that will guide our development and analysis of the structured procrastination algorithm for selecting a near optimal configuration. So the first key theme is concentration of measure. This refers to the phenomenon asserted by the Hoeffding bound, that when we've drawn a large number of samples from a distribution, we can put down a reasonably narrow confidence interval and know that it contains the true mean with high probability. And the second theme of the analysis is something that I would call process of elimination. It refers to a little bit of indirection that I did in the analysis of this algorithm, where instead of directly showing that it outputs an epsilon optimal arm, I show that it cannot output an epsilon suboptimal arm because it could not have devoted a large share of its time budget to pulling any one of the suboptimal arms. And therefore, by process of elimination, most of its time budget was spent on the near optimal ones. So that kind of indirection where we bound time spent on the suboptimal configurations and use that to assure ourselves that we have mostly allocated our resources to testing the near optimal ones is going to be a recurring theme in the remainder of my lecture and in Devon's. Screen sharing has stopped as the shared window is closed. I must have closed it by accident, and let me rectify that. Now that I've had so many technical difficulties, it's a good time for me to ask Yisong, what's the time budget for this lecture?
The total budget is an hour and a half. So you're at about 32 minutes total remaining. I think if you need to go slightly over time, I think, of course, it's recorded and many people watch it offline, so I think it's totally fine.
Okay, I'll try to hurry up then so as not to go too far over. We're now getting to the point where we want to apply these ideas to design an algorithm configuration procedure. Our plan of attack is going to be to adjust the UCB algorithm that I just presented to you. And there are three differences that we need to account for. One, we're doing minimization rather than maximization. So we will use a lower confidence bound instead of an upper confidence bound. We want to get a multiplicative rather than additive approximation to optimality. That will require us to use a different concentration of measure principle called the Chernoff bound rather than the Hufting bound. And the most interesting difference is this ability to cap the cost of pulling an arm at theta. That's where I'll focus most of our attention. So here's what the Chernoff bound says. It's like the Hufting bound, but it deals with multiplicative error instead of additive error. But the specifics of how the bound looks are more or less the same. The probability that the empirical mean after S samples deviates from its expected value by a factor of worse than 1 plus or minus epsilon is bounded by something which goes to 0 exponentially in the number of samples. And I guess the only difference that I really want to bring to your attention is that the sample complexity of getting a multiplicative approximation is order mu to the -1, epsilon to the -2, instead of merely epsilon to the -2. And this reflects the fact that probabilities of rare events are hard to estimate. So if these random variables are supported in 0, 1, but their expected value is 1 over a million, then it really does take an enormous number of samples to get a good multiplicative approximation to that probability. Because, for example, until you've drawn 1 million samples, you don't even expect to see the event happen even once, let alone enough times for you to accurately estimate its probability of occurrence to within small multiplicative error. For that reason, it's often useful to work with a variant of the Chernoff bound, where the exponential bound on the right-hand side refers to a predefined quantity m rather than the possibly unknowable actual mean value of the distribution. Okay, so here I have the version of the Chernoff bound where we're given IID random variables, we're given some sample complexity S, and we're given some threshold quantity m. And we want to be sure that if m over s is significantly bigger than the mean of the distribution, then it's very unlikely that the sum of the values is going to be greater than m, and a similar bound for undershooting the expected sum. And okay. Again, we get an exponentially small probability of failure, where now the exponential is in -m and no longer has any dependence on mu. So this is a useful variant of the Chernoff bound when you don't know the exact expected value of mu. And informally, what it's saying is, if you don't know what fraction of lottery tickets are winners, but you bought 1 billion random lottery tickets and 1,000 of them turned out to be winners, you can be pretty sure that the actual rate of winners among lottery tickets is multiplicatively close to 1 in a million, because the probability of that empirical frequency being far off from the true frequency of winning lottery tickets is exponentially small in the number of winning tickets you've seen, 1,000. Okay. So this is the concentration of measure principle that we're going to use in our algorithm. And here's the basic scaffolding for the algorithm. For each algorithm configuration we're going to have a configuration tester procedure. And when queried, this configuration tester should be able to report a lower confidence bound for the configuration that it is testing. When prompted to get more data, it should decide to perform one more run of that configuration, which means it has to select an instance to run it on and a timeout threshold. And then when the run completes, the configuration tester is going to update its lower confidence bound estimate. To specify the algorithm, of course, I have to explain how each of these steps is done. How do we calculate the LCB? Which instance J and timeout threshold theta do we choose? But then after specifying those details, the algorithm is going to work by running a main loop where in every iteration of the loop, we ask each configuration tester for their LCB. We select the one with the smallest LCB. We prompt it to get more data. And that means that in order to finish designing the algorithm, we just have to answer a few key questions. The biggest one is when we decide to obtain more data about a configuration, should we test a fresh problem instance? Should we retest one that it previously failed to solve because we didn't give it enough time? And in either case, what timeout threshold should we use? Okay, so this is actually, this question one is the main point where algorithm configuration differs from multi-armed bandits, because when you decide to pull an arm of a bandit problem, there's nothing else you have to decide. There's no other operation you can do but pull the arm and get one more random sample of its payoff. When you decide to get more data about an algorithm configuration, you have to make all these subsidiary decisions about in what way to get data. And there are trade-offs to setting a high timeout threshold, which could be costly, a low one, which is more likely to result in a censored observation, which is less useful to you, etc. We also need to answer how to compute these lower confidence bounds, and also when the user stops the search and asks us to propose a near optimal configuration, which one should we select? Okay, so here's how those questions are answered in our algorithm. The first one is the most interesting, and I'll actually go into greater depth on that in the following slides. The lower confidence bound, we're just going to multiply the empirical average by a factor slightly less than 1. And the Chernoff bound will ensure that this lower confidence bound is unlikely to fail to be well calibrated as long as we're averaging enough samples together. And when we are asked to stop the search and propose a near optimal configuration, we're just going to select the one whose tests have consumed the greatest total running time so far. This is ironic and counterintuitive because we're trying to select a configuration that runs fast on average, but we're selecting the one that has run for the greatest amount of time so far. But the justification for that counterintuitive rule is this process of elimination form of reasoning, that our search procedure is going to be designed so that it does not waste much time on any of the suboptimal ones. Therefore, if it has spent a lot of time testing configuration I, it can only mean that I is near optimal, or that we're in an unclean execution, which will be a low probability event. So the way we manage our queues is for each configuration, we have a double-ended queue. An element of the queue consists of an instance and a timeout threshold. And when prompted to run configuration tester I, what we do is we pluck an element off the head of the queue. We try to solve that instance j with timeout theta. If it succeeds, that's great. We got one more data point. If it fails, we double the timeout threshold and stick it into the back of the queue. This explains the name structured procrastination, because we're procrastinating on solving the instances that are really hard to solve. And they just accumulate in this queue that gets longer and longer over time with doubling thresholds. Okay, there's an icky formula for the length of the queue. And of course, the icky formula is governed by the fact that we're eventually going to plug it into the Chernoff bound, and we want to get a number that it will be nice to work with coming out of that formula. And finally, sometimes the queue needs to be replenished because, for example, we solved one of the instances that had been hanging around in the queue. We finally gave it enough time that it ran to completion. So now we have one fewer element in the queue than desired. When that happens, we just randomly sample a fresh instance and plunk it into the head of the queue using the same timeout threshold as the previous element at the head of the queue. This queue management protocol ensures that at all times, all the queue elements have timeout threshold equal to either theta, the value at the head of the queue, or 2 theta, the double of that value. They're arranged in order of non-decreasing timeout thresholds. And any instance that was previously in the queue but has now been completely solved must have been solved in time theta or less. These are just simple loop invariants of the queue management procedure that I defined. And the analysis is based on defining a notion of clean execution that generalizes the clean execution for multi-armed bandits. So in a clean execution of this algorithm, the estimates of average running time, empirical estimates of average running time, have to be multiplicatively close to their true value. And the empirical estimate of the probability of finishing before cap time theta also needs to be close to its empirical value. Okay, but using the Chernoff bound as before, it'll be easy to show that by union bound, all of these events happen with probability at least 1 minus zeta. And so that reduces the analysis of this algorithm to analyzing what happens during a clean execution. That analysis resembles the one I presented for UCB in the sense that the next thing to do is think about a suboptimal configuration and do some algebra to convince ourselves that we simply cannot spend a lot of time testing that suboptimal configuration, because after we have expended a certain minimum amount of time, we must have collected enough, in a clean execution, we must have collected enough samples of its running time to have confirmed that it is epsilon suboptimal. And after that, we would never have scheduled it to be tested again. And so the analysis finishes up in the same way that the analysis of UCB finished up. If the total amount of running time devoted to the search procedure is bigger than the bound in blue, then once we subtract out the maximum amount of time that could have been allocated to suboptimal configurations, we know that the remaining time must have been split into some shares allocated to the near optimal ones. And by the pigeonhole principle, that means that at least one of the near optimal configurations must have run for a greater total amount of time than any of the suboptimal ones. Therefore, in a clean execution, when you interrupt the search and ask it to predict a near optimal configuration, you can be sure that it will predict correctly as long as t is above this bound. I guess the salient features of this bound to me are its inverse quadratic in epsilon. And that is no surprise, because anytime you want to estimate some random quantity to within epsilon multiplicative error by random sampling, you typically have to draw at least epsilon to the -2 samples. It is, there's a factor of 1 over delta per configuration. That's because that refers to the fact that we're throwing out black swan events that occur with probability less than delta to be sure that if there was a, brown swan event that occurs with probability in between delta and 2 delta, we still would have caught it. To ensure that, we need to get at least 1 over delta samples of each configuration. And finally, the time scales linearly with the runtime of the optimum configuration. That makes sense because you can't discover a near optimal configuration asymptotically faster than the time it takes to run the optimal configuration to solve at least 1 instance. So each of the factors inside this expression sort of information theoretically needs to be there. And in our IJCAI paper in section 6, we show that actually the product of all those terms is information theoretically unavoidable. So in the worst case, if you want to write down a bound in terms of n, epsilon, delta, and the optimum runtime, except for log factors, you can't asymptotically improve the bounds that I just presented to you. And this is actually my last slide. There's a final point I wanted to make about how we deal with the case of an exponentially large or infinite set of configurations, which, as I said earlier in the talk, is important because algorithm configuration problems typically do have a very high dimensional hyperparameter space of configurations. And the best thing that we in our paper were able to say about that is, if you want to find a configuration which is competitive with the top 1% of configurations, then you can just randomly sample 1,000 configurations from this exponentially large or infinite space. You can be confident that with high probability, 1 of your 1,000 is among the top 1 percentile of all configurations. And then you can run the finite configuration tester that I presented to you to find one which is nearly as good as the best among the 1,000 that you sampled. So there's kind of a generic reduction from the case of an infinite search space to the case of a finite search space, if you're willing to accept that the definition of success is just finding something which is near the top gamma quantile of the infinite search space of configurations. However, that is kind of a lame way of solving the problem with a large space of algorithm configurations. And in other work that I have not been a part of, which is more oriented towards practical performance and less toward proving theorems, there are quite sophisticated model-based local search procedures that people have used to kind of once they find, perhaps by random sampling, a relatively good point in the parameter space of configurations, then they can do some kind of local search and use more assumptions about the structure of this high dimensional configuration space to improve in a neighborhood of the moderately good configurations that they initially found by random sampling. And in practice, this works much better than just uniformly random sampling 1,000 configurations and trying to figure out which of those is best. So in short, our paper has something to say from a theory mindset about what to do when you have an exponentially larger infinite set of configurations, but the theory does not yet seem to have caught up with practice or even come within striking distance of it yet. And that's an interesting open question for future work. I'm done with my spiel. I apologize to Devon and to the people in the class for having used more than my fair share of time.
No worries. Devon, why don't you
Sure. I'll just dive right in. Okay, can you see my slide there?
Yes, we can.
Great. And how about my cursor? Can you see that? That'll be helpful.
Yeah, we can see the cursor.
Okay, cool. Okay, yeah, so thanks, Bobby, for that great setup, and thanks Yisong for having us and including our work in your course. I'm going to talk today about an algorithm called structured procrastination with confidence. And so this is follow-up work to what Bobby has talked about, again with Kevin and Brendan, and this time myself as well. And so the main difference is we replace the sort of sample mean in the algorithm with a novel form of lower confidence bound, hence the name. So first I'm going to talk a little bit about just sort of some properties you might want from a theoretically sound algorithm configuration procedure. Then I'll contrast structured procrastination with SPC and show how they're different. In doing so, I'll talk about this lower confidence bound that I mentioned, and show how this allows us to get a better runtime guarantee than structured procrastination. Just show some quick plots from a simple example, and hopefully get to some current and future work, only because Bobby set me up so perfectly for that, although in the interest of time, we may skip that. So, what kind of things might you want from a theoretically motivated configuration procedure? So I kind of think of these as two different categories. The first are kind of the basic guarantees that every configuration procedure needs, things like correctness and some sort of guarantee on runtime. These are pretty basic for a theoretical algorithm. I also consider this some sort of applicability to an infinite configuration space to be important. This is sort of what Bobby was talking about briefly at the end there. And just because this is sort of the real world scenario that you often find yourself in, pretty much every algorithm has at least one continuous parameter. So all of the, you can see structured procrastination checks all of these boxes, as does SPC. There's this other line of work that I won't talk about, especially in the interest of time now. But I encourage you to look at it yourselves if you're interested, from a group at DeepMind who, following the structured procrastination paper, adopted the same optimality definition and developed these very different style of algorithm for solving the problem. So in particular, the algorithm caps and runs is cool, and it improves on the runtime bound in a few ways. But that's all I'm going to say about those for now. So there's this sort of second class of properties that you might want. The first is an anytime algorithm. And so Bobby talked a little bit about this. He mentioned it in the context of bandits. And the second one is a sort of adaptive runtime bound. So this is like beyond worst case analysis. And as you can see, structured procrastination has this anytime guarantee, but not the adaptive runtime bound. The others, it's reversed, and structured procrastination with confidence is able to achieve both of these things. So I'll talk a little bit more about what these mean now, and why we kind of would want them. So, Bobby kind of touched on this already, but a configuration procedure takes this parameter delta as input, and it might not always be easy to know how to set this. Like, it's not an intuitive parameter. It's has to do with how much of your tail probability you're willing to disregard. And in particular, a user might not even know what tail probability means, So the anytime algorithm, instead of taking it as input, just starts with a high value of it, like delta of 1, and gradually refines this as the procedure goes on. And then when the user stops the algorithm, it gives the best guarantee it can. Okay, so this is a nice property from a usability point of view, but it also can actually speed up the process of finding an optimal configuration. in that, really bad configurations might be able to be kind of discarded at a larger value of delta, and more cheaply than if they would have been discarded at a smaller value of delta, if that was your sort of target value. So it's nice from a usability point of view, but it also can actually speed up the procedure. Okay, and the property I really want to talk about is this adaptive runtime bound. So as Bobby mentioned, in the worst case, there's this sort of information theoretical argument that any configuration procedure has to take this much time for each configuration it considers. Okay, and it's sort of like you have to run it for at least opt to know it's worse than opt. You need this epsilon squared term to estimate its mean, and the delta to see these rare events that are driving the mean. Okay, so there's no getting around this in the worst case. But maybe in non-worst case scenarios, we can do better. And in particular, we tend to think in the real world, lots of scenarios are not the worst case scenario. And really, we tend to have a few good configurations and lots of really bad configurations. So maybe we can get a runtime bound that, kind of scales with this quality. Okay, so how does SPC differ from SP? So as I've mentioned, it uses this lower confidence bound rather than a sample mean to select configurations. So it's using this same sort of, choosing what looks best at that moment in time principle as SP. But because it uses a lower bound, it's able to only run bad configurations as much as it needs to sort of discard them in favor of something else. Okay, so that's the most important property, and as a result of that, we can show this adaptive runtime bound and essentially argue that SPC only needs to run each configuration enough to sort of separate it from the next best thing. Okay, and in that sense, the runtime for a configuration scales with kind of this measure of how suboptimal it is. Okay, so and that's where the main gains are to be found. Okay, so the algorithm itself is structurally almost identical to what Bobby's already presented. So I have it written here, but I'll go over it very quickly. But really the main difference is in this line here, where you're selecting based on an LCB rather than the sample mean. Okay. Otherwise, all the elements are the same. There's this Q data structure of instance and cap time pairs. You select your configuration to run. You choose an instance, either by sampling a new one if you can, or if your queue is already at capacity, by rerunning an instance that you've run before. Okay. Same thing, if it times out, you reinsert it with double the cap time. So this is all exactly like SP. Update your lower confidence bound based on the new runs and repeat. Another slight difference is when you're terminated and you're asked to return a configuration, you return the one that's been run on the most problem instances. Okay, so again, this might not be exactly intuitive why we do this, but it has the most instances. That means it was likely to be selected in many iterations. And so it tended to have a small LCD, and it was run a lot. So we're pretty confident that this LCD is tight. And so that's the kind of intuition.
Can I ask a quick question?
Yeah, please.
Yeah, so I must have missed it if it was talked about earlier, but is there any trick or any nuance to the length of the queue?
Sure. So I totally have ignored that. Bobby did mention it. I think at that point he was feeling the time pressure, so he skipped it pretty quickly. Essentially, though, it's set to have this kind of log something over epsilon squared term. In structured procrastination, it's a little different because the probability guarantees are tweaked. But essentially, it's set to get this guarantee, the high probability guarantee. Okay, cool. But I mean, great question. That kind of controls, in a sense, explore versus exploit. You know, it's like if your queue has length only 1, you're just going to keep running the same instance again and again and again until it completes. But if it has infinite length, you'll never rerun anything that times out. And so finding this balance is kind of like crucial.
Okay. If I could cut in, I think that the one nuance that I would say can often fail to come through on a first skimming of the paper is this thing I was saying about when you're trying to use the Chernoff bound to estimate the probability of a winning lottery ticket, it doesn't matter how many lottery tickets you bought. If 1,000 of them turned out to be winning tickets, you can be quite sure that the expected number of winning tickets in that total pool was somewhere between, that the expected number of winning tickets in a total pool of the same size would be between 900 and 1,100 the next time you run the experiment on a fresh pool of the same size. So the way that relates here is one of the things that SPC is trying to do is estimate the probability that configuration I times out on fresh test instances with cap time theta. And so the empirical rate of timeout is queue length divided by the total number of configurations I've ever tested with I. And you might think that what matters for estimating that empirical rate of timeout is the total number of samples I've ever gotten, but it's not. What really matters is the number of times that the rare event has happened, the number of times the timeout event has happened. That number is captured by the queue length. And so it's the queue length and not the total number of samples that actually determines whether the Chernoff bound is going to be strong enough for you.
Okay, thank you.
And that's why the queue length has to be given by a very specific formula that plugs directly into the Chernoff bound.
Yeah, cool. Okay. Thanks, Bobby, and great question, Yisong. And in general, if there are other questions, feel free to interrupt. Okay, so I've talked a lot about this LCB, but I haven't said anything about what it is yet. So let's talk about that. So in order to understand it, we need to first remember this fact from like elementary probability theory, and that is that the expected value of a positive random variable, at least, is the area above its cumulative distribution function. Okay, so the line here is the CDF of a runtime. Then the expected runtime is the area here in blue, and that's the kind of quantity we're interested in estimating for these for each configuration. Okay, so our lower confidence bound will be based on this sort of computation of the mean. Okay, so this pictorially represents the way we are computing this lower bound. So again, there's the true CDF here in blue, and the true expectation is the area above it. Of course, we don't get to observe the true CDF. Instead, we observe some samples and this empirical CDF, okay? And so the lower confidence bound, of course, will be based on this empirical CDF instead. And the form it has is kind of, again, an integral over this step function, which turns out to be like just a finite sum over your samples that you've taken. And each term in that sum is 1 minus the empirical CDF, which is like this height here between the CDF and the value 1, and some scaling factor. Okay, and the scaling factor shrinks this quantity slightly. And so that's why you can see that our lower confidence bound, this region here in green, is like, has been sort of scaled down at each step of the CDF. Okay, and the scaling factor I'll talk about briefly, but essentially it's set so that it converges to 1, basically, so that the lower bound converges to the true runtime with more and more samples. And it's set to do larger scaling at higher runtime values, so at areas where the CDF is closer to 1. And this kind of captures the idea that we're less certain about things further out in the distribution than we are about the kind of shorter runtimes. Okay, so that's the idea in pictures. You might say, like, why does it have this kind of strange form? And to answer that, I introduced this theorem quickly from empirical process theory due to Wellner. And essentially, this is a theorem about how close an empirical CDF is to a true CDF. Okay, and so based on in this case R, IID samples from that distribution, how sure can, or how close can we say we are to the true CDF? So it's a bit of a strange form, but you kind of take these two parameters, and in the back of your head, I want you to be kind of thinking about the Chernoff bound that Bobby's talked about, and basically what we end up with is something that has a very similar form here, right? It's sort of saying, okay, either our sampled empirical CDF is very big, like kind of close to 1 or something, or it's a really good approximation of the true CDF. But that's for every point X along the CDF, okay? So it kind of, this theorem gives us a Chernoff type bound at each stage along the CDF of the runtime, okay? And so this is why we use the bound we do. And so the idea will be to apply this theorem by setting, you know, C and epsilon in the same sort of way that Bobby's talked about in terms of, you know, making this probability quantity here work out to the sort of thing we want. Okay, and just the kind of cartoony proof of how setting this ensures that we get a lower bound that we want is found here. And really the punchline is that this scaling factor is set to kind of shoehorn everything into that theorem of Wellner, okay? And it's like, you know, see paper for details. There's a lot of detail in how these are chosen, and in particular these two cases, and you need to sort of worry about, in this guy, the case where you're close to 1 and you don't have this guarantee, but as I say, these constants are just sort of chosen to make it all work out. Okay, so we end up with this lower bound that is indeed a lower bound, and, you know, converges to the true thing with more samples, and so we're happy. And the main gain that we get from using this bound is in this key lemma. And so essentially what this lemma says is SPC won't waste too much time testing bad configurations. Okay, we're able to get a bound on in particular the number of instances that an epsilon delta suboptimal configuration is run on. Okay, and knowing that we spend minimal time on suboptimal configurations allows us to make this sort of like pigeonhole-y argument that Bobby has talked about, that's saying, okay, well, if you didn't spend too much time on the bad ones, like some good one must have received a lot of attention. Okay, and the proof again is very similar to this sort of you can estimate your mean through sufficiently many samples with good probability using a Chernoff type bound. And so we know this lower confidence bound is a good approximation of the true mean. And then this kind of selection argument saying, well, if it's not good, it can't have been selected too many times. Okay, so I think I'll leave that at that for now. But as I say, the important thing is that we know we spend minimal amount of time on suboptimal configurations. Okay, so that gives us a theorem that's very similar in style to what Bobby talked about for structured procrastination. Let's not worry about the actual time here for a second. I will talk about that in the next slide, but basically it says, if you run SPC for this much time, then it's guaranteed to output an epsilon delta optimal configuration, okay, with high probability in the number of steps it's been run for. And again, the proof is similar to this sort of pigeonhole argument. We know from before that you're spending a minimal amount of time on suboptimal configurations. Therefore, there must be some optimal configuration in this set which has received a large proportion of your attention and has therefore run on many instances. And so at the end, when you return the configuration that's run on the most instances, you can be sure that it's run on more instances than any suboptimal configuration. Okay, and so the kind of the proof is pretty different, but the kind of logic underlying it is the same as what Bobby's already talked about. Good. So what about this quantity here? It's a bit hard to interpret, maybe, but if we can compare it to structured procrastination. If we ignore like logarithmic and constant factors, as Bobby showed us, we kind of have, we run sort of opt over epsilon squared delta for each of the configurations we consider. And this is great, it matches the information theoretical worst case lower bound. And so this is like up to log factors optimal in the worst case. But again, not all configurations are the worst case. And so SPC is able to split out these two classes of configurations. So it's still paying this cost for all of the epsilon delta optimal configurations. These are the ones that it kind of can't tell apart based on the parameters epsilon and delta. But it's paying this reduced cost for the suboptimal ones. And in particular, it's scaling with this quantity epsilon I delta I, where epsilon and I and delta I are the largest possible parameters for which I is still suboptimal. Okay, so when a configuration is really, really bad, that can be a really huge saving.
I have a quick question. So epsilon is chosen by the algorithm designer, right? Epsilon.
Well, so in structured procrastination, it is. In structured procrastination with confidence, it's not.
I see. Okay.
It's kind of rolled into the anytime guarantee with delta here.
Okay.
Okay. yeah, there's tons more I can sort of say about that in terms of the epsilon and delta that you're guaranteed between the two algorithms. But yeah, it's in SPC, it kind of treats this quantity as one parameter and it refines it sort of uniformly. Okay, so the main takeaway here is we get this saving for suboptimal configurations. Okay, and so just to demonstrate this, I ran some, generated a couple hundred configurations with exponential runtimes, and in their means drawn uniformly between opt and to opt. Okay, and you can see, so on the x-axis here is their mean, the mean of the configuration, and on the y-axis is the number of seconds the configurator spent running it. And you can clearly see, so blue is structure procrastination, and it's really just running everything for the same amount of time, right? Somewhere around 11,000 seconds. Whereas SPC has this nice upward slope, and so the better configurations with smaller mean are really receiving more attention. And so this is exactly demonstrating that bound that I've been talking about. And if I increase this to be 5 opt instead of 2 opt, it's only more pronounced. You see SP is still sort of running everything around 11,000 seconds, but SPC is really starting to focus in on these few configurations and dedicate like the majority of its time there. And one more step, it's even hard to see, but the scale has kind of like doubled here. Okay, and so, but still SP is just really giving everyone the same amount of attention. Okay, so this is sort of synthetic demonstration of exactly this runtime property. Okay, so I do want to talk about this very quickly, just because, as I say, Bobby set me up nicely. This is sort of what Kevin and I have, and another guy in our group have been thinking about recently. The definition of optimality had these two parameters, epsilon and delta. Epsilon is a kind of intuitive parameter that you can understand as a user. It's like, okay, I don't care if my solution is maybe twice as fast as optimal, but 3 times is too much. But delta is less so. It was kind of included to handle this really heavy tail case that's a bit, I don't know, not even clear maybe how we want to handle this case. And so, if you consider these two configurations, it can be illustrative, I think. So the first guy, in 1 in 100 runs, it takes 100, say, minutes to finish. Okay, and then for 99% of the runs, it finishes like instantaneously. Whereas the second configuration finishes in 1 minute on everything, deterministically. So these two configurations have the same mean, right, 1 minute, but this configuration is faster 99% of the time. So maybe we don't want to treat these two configurations the same. And delta is a way to do that, but only if delta is sort of set properly, right? And that's just kind of begging the question, because you could set delta, but then I can just choose OK 200 instead or something like that. And in reality, we kind of tend to think this configuration is better than this one. Like maybe 1% of the time I'm willing to just ignore what happens and do some sort of default behavior. And I think that this, and a practitioner would, I think, tend to agree with me from conversations I've had. So maybe we can redefine this objective, define some sort of notion of the utility that we gain from doing a run of a configuration on an instance. And maybe in doing that, we can maybe weight our preference for this configuration over this configuration appropriately. And then look at kind of an expected inverse utility or something like that. Okay, so the last thing I want to say is just returning to this slide and saying, there's lots more to think about here. Bobby talked a little bit about this being anytime of this gamma parameter that allows you to search an infinite configuration space. How do you know at any given point if the best thing to do is sample a new configuration or improve your understanding of existing ones? And so maybe there's a smart way to sort of trade these off throughout the execution of an algorithm. And finally, you know, algorithm configuration without theoretical guarantees has been around for a while, and they have had great success. So maybe we can kind of steal some of their tricks. And that's all I have to say, so thanks.
All right, thank you, Bobby and Devon. I think in the interest of time, we'll just end the lecture here. Thank you so much for taking the time to present your very interesting work.